Hi, welcome back to McClatchy Maths. My name is Natalie McClatchy and today we are starting a new playlist on Surds. But before we get started, here's how you can engage further with us here at McClatchy Maths. First thing you can do is like and subscribe and hit that notifications bell up top so you'll always know when the next video is available. You could tell someone about this video, why not share it in your OneNote or click the little arrow button that enables you to share the link to the video with a friend or a family member. There's also a new feature on YouTube called Super Thanks. It's a little love heart button that you can click and donate $2 to keep the channel going. And you could also follow us on social media. We're on Facebook and Instagram. Okay, so let's have a look at what we're going to be covering in this video. We're going to define what a surd is. We're going to look at how to simplify surds. There'll be some worked examples and then we'll have a quick chat about what's coming up in the next videos. Okay, so first of all, we need to have a think about our number system. Our number systems can be grouped, different types of numbers can be grouped into different categories. So we have something called rational numbers, and this is any number that can be expressed as a fraction. So things like the number 3 can be expressed as a fraction, 3 over 1, because 3 divided by 1 is just 3. Normally we think of whole numbers as just whole numbers, but they are actually fractions as well. We've got other things like decimals, like the number half can be expressed as 0.5 or 1 over 2. We've got things like a quarter, which can be expressed as 0.25. So as long as it can be expressed in some sort of fraction form, it's called a rational number. Now, rational numbers, as I've mentioned, can also be in decimal form or fraction form, but with decimals, they have to be what's called a terminating decimal. So in the example over here with 0.5, it's what we call a terminating decimal because it stops. That's what terminate means, to stop. So it stops at the digit 5 in the tenths column. We've also got something called recurring decimals. An example of that is the number 1/3. It can be expressed as a fraction, 1 over 3, but as a decimal it's expressed as 0.33333 and on into infinity. So recurring means it repeats that number 3. So we've also got some other examples here. Whole number 1.6, that can be expressed as 1 6/10, or 1 3/5 if we were to simplify the fraction. That's what we call the terminating decimal because after the 6 there's no more values except for the value 0, which we don't need to write down. And I've given that example of 0.33. This little dot above the 3 means it repeats. When I was growing up, it was called a repeater. So that little dot there, it can also be expressed with other symbols as well, like a bar. Now, that is a recurring decimal because that 3 goes on and on into infinity and it repeats or recurs. So these are all our rational number system. Now, irrational numbers are ones that can not be expressed as fractions. For example, we've got the number pi. Pi is 3.14159 and the numbers go on into infinity with no repetition at all. So that cannot be put back into fraction form. Now, of course, you've probably seen things like pi being expressed as 22 over 7. It's not exactly that number though. There's a more exact form for pi and it is an irrational number. They have an infinite number of non-recurring decimal places. Now, we represent a surd by using what's called a root sign or a square root sign. It looks like a tick, and basically all the numbers under here, there's a flat line that will sit on top of those numbers. And so this will be a whole number under the square root sign, not a decimal number. So here is some examples of some irrational numbers. These are all prime numbers. All our prime numbers can only be divided by the number n itself. So all our primes are going to be surds. But we also have some composite numbers. Composite numbers means it's two numbers multiplied together to make that number. Like 6, for example, is 3 times 2, and 8 is 4 times 2, and 10 is 5 times 2. So these are all composite numbers, but they're also all surds. Because when we take the square root of these numbers, there will be that infinite number of non-recurring decimal places. So what we need to remember is that a surd must be irrational when we evaluate the square root. What I mean by that is when you put that number in your calculator and press the equals button, and most calculators you're going to press the square root sign first on your calculator, then type the number in, press equals, it's just going to go on into infinity. Now, when you look on your calculator does round to sometimes 8 or 10 decimal places, so be aware that even though it's rounded off, it will still be potentially a surd. You'd have to know some of these things off by heart. For example, I know off by heart probably the first 30 or 40 surds. I could list them off. I'm not going to do that, it'll be boring. Okay, so some other numbers are not surds because when we actually do the square root on our calculator, we get a rational number. So the square root of 4 is made up of 2 times 2. So the square root of 4 is 2. It's 2 multiplied by itself. So the square root of 4 is 2. That's a rational number. The square root of 25 is 5 squared, 5 times 5, and so the answer is just 5. So when we do that on our calculator or do it in our head, we're going to get a whole number or a fraction that is not an irrational number. It'll be a rational number, so that means they are not surds. Okay, let's have a little talk about some surd rules, which is going to help us as we move forward in our video series and also as we look at how to simplify surds. So our first rule is when we square a surd, the answer will be the number under the square root sign. Now, it's always helpful to look at that with a picture. So I'm going to start with some algebra first. So if I've got this surd here, the square root of x, we don't know what that number is. It's any number that will make a surd up, like the square root of 3 or the square root of 5. When we square it, this square root sign is undone by the squaring. They are the opposites or the inverse of one another. So the answer will be simply x. If I had a pencil, I could cross out the square root sign and cross out the squared sign because they're being opposites or the inverse function, they will cancel one another out. So the answer will be the number under the square root sign here, which is x. Another way of expressing that without the brackets is the square root of x squared. The square root sign is cancelled out by the squared sign and it's simply x. Now this only happens where x is greater than or equal to 0. We don't, in this series, have negative numbers under square root signs. So they will not be surds. So that's why this always needs to be greater than or equal to 0. So you can't find the square root of a negative number. That's just something to be aware of. So the square root of 5 squared. Let's look at this with some numbers now because some people find it a little bit abstract looking at it with letters. If I took the square root of 5, now the square root of 5 is a surd. I call it often, I'm a little bit lazy, I call it root 5. And your teacher might call it square root 5, or they might call it square root of 5, or they might just say root 5. And in my video series, I'm just going to be saying root 5 to save time, okay? So if I had root 5 and I squared it, well, this square root sign and this squared number will cancel out, and then I'm left with just 5. So this is our first surd rule, something important to know. And another way of thinking about this is if you've watched our index laws series, you'll know that when we can re-express a square root of something as something with a power. It's a power of 1/2. Now, if you remember your index laws, and we covered that with fractional indices in one of those videos there. So 5 to the power of the half, and then we've got these brackets, and then we're going to be doing the 2, we're squaring that. So if you remember your brackets rule, which is index law 3, if we've got to the power of a half here, and then we square it, half of 2, half times 2 is just 1, 5. That's why this rule works. So that's what this would look like. So 5 to the power of 1 is simply just 5. That's where that rule comes from. Second surd law is that if a surd is made up of 2 numbers multiplied together, we can break those up as separate surds. So what I mean by this is if I've got the square root of x and y, I can rewrite that as the square root of x multiplied by the square root of y because there's a little invisible times symbol in here. And once again, this only works where x and y are greater than or equal to 0 because we don't do surds with negative numbers. So for example, if I've got the square root of 26, I could rewrite that because I know 26 is also made up of 13 times 2. So I could rewrite that as the square root of 13 times the square root of 2. So this is an important skill that will enable us to simplify surds when we get to that part of this video. Our third surd rule is that if a surd is made up of a fraction under a square root sign, then we can re-express that fraction as a surd on the top as the numerator and a surd on the bottom, which is the denominator. So that would look like this. If I've got this fraction underneath the square root sign, I could rewrite that as the square root of x and the square root of y, once again, where x and y are greater than or equal to 0. So another way of looking at that with numbers is the square root of 5 over 2. I can rewrite as the square root of 5 divided by the square root of 2. Okay, now we're going to talk about simplifying surds. So those surd rules are going to enable us to simplify them. And if we've got a surd that is made up of a composite number and 2 numbers multiplied together, then if one of those numbers is a perfect square, we can simplify the surd. Now, you might be wondering, what does she mean by perfect squares? Well, one way of thinking of that is to go through from the number 2 and just move up. 2 squared is 4. 4 is a perfect square. 3 squared is 9. 9 is a perfect square. 4 squared is 16. 16 is a perfect square. So if you know your numbers, maybe up to the number 12, 2 squared, 3 squared, all the way up to 12 squared, and some other ones like 20 squared, 15 squared, it makes it much easier to work out if one of those perfect squared numbers is a factor of our original surd. We can simplify that surd further. So we're going to start with our first worked example, and we're going to simplify the square root of 32. Now this is where I want to be thinking of those perfect squares. So I know that, well, for example, 8 times 4 is 32. I know that from my times tables. And this is where, as we're getting into senior maths, knowing our times tables is really important. Now, out of 8 times 4, 4 is a perfect square. I could use that to simplify the surd. Alternatively, I could go bigger. 16 times 2 is 32, and 16 is also a perfect square. So that's root 32, we're going to go with that one, is made up of root 16 times the square root of 2. So we've taken this number here, we've broken it up into a factor pair. And we can simplify that further, remembering that other surd rule we just talked about a few minutes ago. Break those out into 2 separate surds now. Now I know that the square root of 16 is 4, so this becomes 4. I can't simplify that any further because it's root 2, it's a surd. So now I'm left with 4 multiplied by root 2. Now, as you would know in maths, we're a little bit lazy at times. We like to take shortcuts, and especially with the multiplication symbol. So we can ditch that now and simply write our answer as 4 root 2. Let's look at our second example. Simplify 3 root 200. Well, once again, I'm going to break this up, the number 200. I know that's made up of 100 times 2, and I know 100 is a perfect square. So I'm going to break that up. The 3, you'll notice, stays outside the front. That just means 3 multiplied by the square root of 200. So now I've got under my square root sign 100 times 2, and I'm now going to break this into 2 separate surds, like we did in our previous example. And now I can simplify this part here. The square root of 100 is 10. So now I've got 3 times 10 times root 2. And now we're actually going to evaluate the 3 times 10. We know 3 times 10 is 30 times root 2, and we don't need to write that times anymore. We can just 30 joined onto the surd of root 2. Okay, we're on to example 3 now. We're stepping up that complexity a little bit more. We've now got a fraction. 5 root 300 all over 6. So if I had an even number up here, I could simplify the fraction on the outside first if I wanted to. We'll save that to the end. So that's a step I could definitely do. What I've also got here though is I want to focus on this surd part first. And it's a big number, so I need to remember it's made up of 3 times 100. So I can simply write 5, and then I've got my square root sign, 3 times 100 all over 6. And now I'm going to break out this surd here into 2 separate surds. So I've got 5 root 3 times the square root of 100 all over 6. Now I can evaluate this. I know the square root of 100 is 10. So now I've got 5 times 10 root 3 over 6. And 5 times 10 is 50. So I've got 50 over 6 with the root 3 here as well. Now this is where I can simplify this fraction on the outside. I can't do it with this surd underneath. That's a big no-no, because this is not 3 over 6, which makes a half. This is root 3 over 6. So I cannot simplify that way because that would be wrong. But I can simplify this way. These are 2 whole numbers. And the common factor for both of those is 2. So if I divide 50 by 2, I get 25. And if I divide 6 by 2, I get 3. So now I've got 25 root 3 over 3. Okay, we're on to example 4, and we're stepping up that complexity a little bit more by looking at our third surd law, where we can break this up into 2 separate surds on the numerator and denominator. So let's do that first. I've now got root 75 over root 9. Now I can simplify that a little bit further. I know the square root of 9 is 3, so that's where I get my new denominator. I've evaluated that. I can now simplify root 75, breaking it out into 2 separate parts, and that's going to become the square root of 25 being 5, will drop down here, and the root 3 there. So I don't need to do that extra step of working every single time if I don't want to. It does create a lot more work for you. If you're good at doing this in your head or doing it straight jumping from there to the next step, go ahead and do it. Otherwise, you might want to insert a next line of working as root 25 times root 3 over 3, and then break it down one step further. But as a teacher, I would accept that as complete working. Let's look at our fifth example here. Now, this is one that's come as a more complex question because now I'm using letters as well as numbers. So I've got a lot more to simplify here. So that's something we're going to have to put our thinking caps on for. Okay, so firstly, we write the question out. And then what I'm going to do is break up what's under here. Now, I know 180 is made up of 36 times 5. Now, you could have broken this up in a few different ways. You could have gone with, for example, 90 times 2 or 9 times 10 times 2 and then broken it out little by little. I always go with the biggest number I can. That's a squared number. So you can practice that on your calculator. See if you can do 180 divided by 16, 180 divided by 25, and so on until you get something you can do. Okay, so now I've broken out the 180 here. Now, I've also broken out the x cubed. X cubed is made up of x squared multiplied by x. 1, 2, 3. And y to the power of 5 is made up of y to the power of 4 times y. This is important. This is where we're going to be using our index laws in a moment. Okay, so let's just do this first part here. The 36, the square root of that is going to become 6. So I'm going to have 5 times 6 will jump out the front. Now, the remaining 5 will not be able to be evaluated, so it will stay under the square root sign. Okay, so that's where we got the 5 times the 6 here and the 5 here. Now, this x squared component, okay, I can take the square root of x and I will simply, of x squared, and I'll simply get x. Because remember, the square root sign will cancel out the 2, the power of 2. So now I've got an x that's now sitting out the front of the surd. And y to the power of 4, remember when we do the square root, where the square root means to the power of a half, so 4 times a half is 2. So now we've got y squared out the front. This is where those index laws come in handy. And what's left behind under the square root sign is this 5, which jumps here, this x here, it jumps here, and this y here. So to simplify that a little bit further, I've got 5 times 6 makes 30, and I've got the xy squared joins together. We get rid of all those multiplication signs, and these two multiplication signs disappear as well, and we can simplify that as root 5xy. So maybe pause here, have a little bit of a think about this one. I think where people will probably find this a little bit tricky is breaking out those cubes into an x squared and an x, and the power of 5 into a 4 and a single y on its own. Okay. We're on to our final part of the video. We're going to be expressing simplified surds as positive integers. What that means is we've just been simplifying a whole lot of surds with some different examples. We're now going to put everything back under the square root sign. So we're reversing. We're doing the opposite of what we've just been doing. So we're complicating the surds as opposed to simplifying them. So the question is going to say that as express it as a positive integer. What that means is I want a surd all under that bracket as a positive number. Okay, so I've got the 2 outside. If I want to get it back under the square root sign, remember it used to be squared and then we cancelled out the squaring and went that way. So now to go back this way, we've got to square it to get it under there. So another way of thinking about that is that 2 is equal to the square root of 4, because the square root of 4 equals 2. So what we can do is we can return that under the square root sign, but we've got to square it first, that outside number, to get it under there. So what I'm going to have over here now is this becomes root 4 times root 5. So another way I could write that is this 5 times 4 all under the square root sign, which is the square root of 20. Well, thank you so much for watching today. If you've got any questions about anything you heard or saw, it's mcclatchymass@yahoo.com. And that's the best place to reach us, especially when you've got detailed questions. Do stay tuned for video 2, where we're going to be looking at adding and subtracting surds. Well, you've been watching McClatchy Maths. I'm Natalie McClatchy. Have a wonderful day.